Federal Rural de Río de Janeiro, la Universidad Federal de Pernambuco, la Universidad Nacional Mayor de San Marcos, la Universidad Nacional de Colombia, la Universidad Nacional de Barranca, el CIMBESTAB de México y obviamente pues con el profesor Stuart también la Universidad de Cambridge y la University College of London. Damos la bienvenida también a a los que van a dar la charla del día de hoy, que sería Jesús Avellaneda y Joan Ibañez. Gracias por el espacio igual que nos dieron para la charla del día de hoy. Jesús, al igual que Joan, son físicos de la Universidad Nacional de Colombia y son estudiantes de la maestría en física de la Universidad Nacional de Colombia. Los dos pertenecen al chapter académico UNMAX, que es de precisamente de la Sociedad Americana de Cerámica, Vidrio y Materiales. Bienvenidos para la charla del día de hoy y cuando ustedes quieran, pues ya pueden comenzar. También invitamos a los que están viéndonos en nuestras redes para que vayan siguiendo la charla y asimismo pues vayan dejando sus preguntas para al final de la charla. Gracias.
So first of all, can you see the presentation?
Yes.
Okay, so first of all, hello, good morning, hi. Welcome to our presentation about our undergraduate work, the material CaLaTiFeO6. In this little presentation, we will discuss the motivation behind this endeavor, the synthesis process, the results, and finally, what's next. So before we begin, a little presentation about who are we. We are parents of students from a wonderful group. You can see the logo right here. In the Universidad Nacional, the physics of the materials group. Our focus is to study different types and responses of materials that we synthesize in-house. And one of those materials is the set CaLaTiFeO6. Due to the Spanish pronunciation, we will pronounce it like that. But yeah, the main idea or the motivation of this work was that initially the interest was finding a material that had interesting or cool properties or characteristics to study. At first glance, we have two materials that are widely studied in the literature and that have quite interesting characteristics. First of all is this right here. It's called lanthanum titanate. And the second one is the calcium titanate. The first for its ferromagnetic properties and the second one for its multiferroic properties. Throwing the formalities out of the window for a sec, if we write down a little stoichiometric equation and operate the whole thing up, apparently, at first glance, these structures can lead to a new one. The set sample, CaLaTiFeO6. First of all, initial calculation using the SPUT software showed us that we had a high enough tolerance factor around 0.95 for two specific structures. Thus, this sample could be synthesized using the quote simple solid state reaction method, which is why this little work began. Also, around that time, Professor Roa suggested that we might be coming across a material that had different valence bands for each spin direction. And taking into account the recent boom in spintonic materials related research, it was worth giving this a try.
So, firstly, we are going to be talking a bit about how we synthesize the material. So, as Jesus said, we synthesize the material by means of a solid state reaction method. In particular, we use the precursor oxides that you can see at the left of the screen. They were lanthanum oxide, which is the second flask, iron oxide, which is the last flask. We use also titanium oxide, which is the first flask, and calcium carbonate, which is the third flask. They were all of them at a really high purity of at least 99.9% purity. And they were the ones that we use for our material. In particular, the solid-state reaction is a fairly straightforward method of synthesis. It occurs at high temperatures on solids and can be easily understood as a diffusion process in which the ions of each of the precursors move due to the high temperature and begin to aggregate into similarly structured oxides. In particular, the diffusion process, you can see, for example, at the right, 3 different mechanisms by which the ions can move in the interface of two materials. In particular, you can see a direct exchange between let's say the material A and the material B. You can have a cyclic rotation of the materials, or you can have a movement through vacancies of the on the defects of the material. So before applying before we could apply the thermal process, we needed to perform a sample preparation in order to increase the probability of the reaction. Firstly, we heated the precursor oxides to remove the humidity that they accumulated because of hygroscopy, I believe. Taking into account that we expected to have a final a perovskite as a final product, we measured the masses of the precursors in order to synthesize a gram of the CaLaTiFeO sample, CaLaTiFeO6 sample. We grinded the material or the mixture inside of an agate mortar for 3 hours and to ensure an increase in the surface contact. And we also made pills with our powder, applying forces up to 50 kilonewton. Okay. Next, so we then proceeded to calcinate our sample with a temperature of about 700 degrees Celsius. This was in order to remove any extra water that we could have in our sample and to promote the production of carbon dioxide and decompressed calcium on the pills. We applied 3 different sintering ramps that you can see the times that we use for each of the sintering ramps at the bottom right. Each of the ramps was of the same shape that we use in the left. We increased from room temperature up to a high temperature value. We kept that temperature for an interval of time, and then we let the material cool down again to room temperature. At the right, you can see the furnaces that we used, the ones that we have at the laboratory in the Universidad Nacional. And it is worth noting that we use alumina crucibles. After each sintering process, we also measured X-ray diffraction and scanning electron microscopy in order to check how the process was evolving. And that's about it about the synthesis. Yep.
Okay, so now let's see how we knew the state of the reaction. First, as my partner said, measurements of XRD patterns were carried out, whose parameters were a step of 0.2 degrees and a zero vacuum. As you and we know, the XRD pattern is one of the most useful tools to evaluate the state of a chemical reaction, and also is like a digital footprint of each material. So if we want to be sure of a complete and successful sintering process, and if we also like to proceed to evaluate other responses of the material, this pattern was essential. So as my friend said, after each sintering process, we also grinded the sample for roughly half an hour, and the resulting powder was sent to the XRD lab, and this cycle was repeated for all the sintering curves. But also, complementary measurements were made to help our understanding of the initial XRD results. As you know, there's not a measurement that gives us a complete picture or gives us all the answers that we want to have when we are studying material sciences. So as you can see in the following images, this was the machine used. In this case, SEM measurements were taken to carry out surface studies to see how the aggregates of the material were evolving with each thermal process, and also to see how the grains of said material were evolving with time. But also to rule out some possible contamination, as you can see right here. EDS was performed, as I said, to see if was some contamination to take into account, or in case to see which kind of contamination there was. Our biggest concern, although it was somewhat expected, was aluminum contamination. Given that the crucible where all the sintering process was carried out was always the same and was made of alumina too, so it can interact with our sample between thermal processes and induce some kind of contamination. But in this case, we didn't have a contamination to take into account. Also, for the magnetic response, or for the magnetic measurements, the UPTC, through Ms. Milena Saavedra and through Professor Carlos Parra, if I'm not mistaken, allowed us to use a BSM to perform the magnetic response measurements. And finally, for the optical response, in this case, it was a plus of the work because we had problems with the electrical response machine. The day that we were supposed to take said measurements, the machine broke. So we thought at that time that we were able to obtain relevant data through an optical response analysis.
Now, we achieved the majority phase, so we are going to be speaking a little bit about the results that we obtained. Here, firstly, the structural properties. At the left, you can see how the diffractograms of each of the processes, both the calcination and the 3-sintering process that we made, evolve through the process. In particular, you can see that first the calcination caused some peaks to decrease in intensity, while in the first sintering, the main peak, the most intense one that is found about 32 degrees, began to form more explicitly. By sintering at 900 degrees, most of the strange peaks disappeared, although the majority phase was not yet present. And with the last sintering at 1100 degrees Celsius, we found some well-defined and intense peaks. And we, in particular, made some kind of a qualitative analysis. We compared our last diffractogram with the precursor oxide, which is the image that you can see at the right, top right, to ensure to a certain extent that we didn't have a lot of precursor oxides left in our sample. And also we try to compare how the peaks of our material compared, or pardon the redundancy, with the possible secondary phases, in particular with the CaTiFeO3 or the titanium calcium, titan, I don't remember, that we expected or that we wanted to add up to CaLaTiFeO6. We performed an additional XRD measurement in which we tried to increase the counts of our diffractogram, in particular in the last diffractogram that we showed in the previous slide. We actually had up to 3,000 counts, so it wasn't enough to make a successful ripple refinement, so we made a new measurement. And the image that you see at the left is the triple refinement that we performed with Jesus. You can see that it is relatively well fitted. We found that we had a chi-squared of 1.35 and a weighted residual of 3.31. In particular, we found the lattice parameters that you can see at the bottom of the screen. And we found that the space group corresponding to our sample was actually a monoclinic set, the P21 over N, which is like a screw axis, if I'm not mistaken. Yep. We found, you can see in the image, the different octahedra, the different inclinations that it has. And we can see, or we found that the glacier notation for the inclinations is actually the A minus, A minus, and B plus. That is, we have two tilts, or if you see through the A direction or the B direction, you are going to see octahedra out of phase. And if you see along the C-axis, you are going to see octahedra in phase. That would be this part. We also measured or made measurements of related to morphological properties. You can see at the left the micrographs for 5,000 and 20,000 magnification after each of the sinterings. That is to say, the A and D are after the first sintering process, with A being the 5,000 magnification and D being the 20,000 magnification. The V and E are the corresponding to the 900 degrees Celsius sintering, and the other two, the C and F, are the last sintering process corresponding to the 1100 degrees Celsius thermal process. And in particular, you can see that this is worth mentioning that in the first sintering, the grains of what seemed to be the majority phase were sometimes too small to distinguish. That is, you can see some white dots that are not entirely well defined. After the second sintering, those white dots began to grow to form the nucleation process that we expected from the solid-state reaction. And after the last sintering process, in which we jumped from 900 degrees Celsius up to 1100 degrees Celsius, we found that basically we had a majority phase. The color was very homogeneous, and so we think that we had completed our process. We thought that we had completed our process. With the images we took at 20,000 magnification, we obtained the grain sizes for each of the sintering processes and found the histograms on the right in order of ascending temperature from top to bottom. In particular, you can see that from the first one, the green one, that is the sintering process for the 850 degrees Celsius, the grain size was relatively well, it was smaller than for the last sintering process, that is the red histogram, in which the grain was noticeably larger. Next. Of the distribution, it is also worth noting that the last one, that is this blue one that I'm showing here, had a larger spread than the other two, and we believe that this is due to the large temperature jump that we made. We went directly from 900 degrees Celsius up to 1100 degrees Celsius, while in the first two sintering process, the difference was only of 50 degrees Celsius. These three photos are three different composition points that we took with these equipment, with the scanning electron microscope. After the last process in the oven, in general, we see that the shape of the grain is almost spherical. And as we saw, was normally solid-state reaction processes. And the grains in this case seem to be trying to stick together. They are trying to fuse, which is, again, normal in solid-state reaction. Since we saw from the histogram that there was only one relevant grain size, you can see that there is only one clear peak. Then we can rule out, for example, several magnetic phases or a high impurity content. That would be the thing about morphology. And now the last thing, we also performed measurements of electron X-ray dispersive spectroscopy to find the composition of our sample. This was made after each of these sintering processes to ensure that we didn't have a lot of contamination. And for the final composition, here in the table you can see the experimental compositions, experimental percentage weight composition of our sample. In particular, they differ from the theoretical by only, let's say, 3% at most. The lanthanum was the one that had the biggest difference, and we believe that this difference was due to the problem that EDS has with measuring the presence of atoms with atomic number smaller than 10. In this case, given that we are working with oxygen, which has an atomic number of 8, then it is possible that it was overestimated or underestimated, and that difference was shown in the lanthanum as well. Yeah, that will be this part. We also found some, we believe that given that we were working with crucibles of alumina, we also found some aluminum in our sample. So it is also worth noting that that could be a source of contamination. Yeah.
Okay, so speaking a little about the results obtained by the optical responses, initially we took the usual curves, absorbance and reflectance measurements, and the data obtained were the basis of the results that we are going to discuss. Initially, what caught our attention was that, as you can see right here, there are peaks in the graphs that should not be initially observed. So with the help of Professor Ra and some literature, we found out that it is possible to associate bond vibration energy with each of the peaks. Basically, when the incident energy is within a certain threshold, this energy causes a vibration in the bonds of the material. These peaks are static, so they can be seen in both graphs obtained. They didn't change position between absorbance and reflectance curves. So that was a curious thing to analyze about. Talking about the neat part, with the data from Rietveld and Vesta, we obtained both bond distances within the material. And as an analogy, let's think of the bonds as if they were strings. So the higher the vibration energy, or the energy that reaches the said bond, the shorter the bond, and vice versa. But as I said, that was a plus analysis for the important analysis of this part. We applied the Kumar method, as you can see the equation right here. As you know, the Kumar method is a relationship between the energy and the reflectance values of the sample that you are analyzing. And this alpha coefficient basically tell us the type of gap that we have. If said coefficient is 2, we have a direct gap, and if it is a half, we have an indirect gap. So as you can see in the graph in the right part, we found that the n necessary for a good data fit was 2. In addition, when we apply the Kumar method, when we adjust the linear part of the process data, it gives us an optical band gap of 0.61 electron volts. So in a first approximation, this will place the material as an electrical semiconductor with a band gap near to other materials known in literature, such as germanium or silicon, if I'm not mistaken. So that was all about the electrical response. In the magnetic response, or for the magnetic response, as I said, the data was obtained from the BSM. The first analysis that interests us was the magnetic moment against the temperature. That is the graph that you can see right here. Basically, if this graph showed paramagnetic behavior that is reversible, then basically there's nothing to do, and we should proceed to study other things. I'm not saying this because we have something against paramagnetic materials, but as we stated previously, we want to have a ferromagnetic behavior. So if we found out that we obtained paramagnetic curves, it was not worth it to start measuring isothermal curves. But as you can see in this case, fortunately, we obtained this curve shown on the left, although this curve is not conclusive enough to exclude some possible paramagnetic behavior. It is a first indication that some interesting things might be happening inside of the material. So basically, what shows us this curve in reality, the figure shows us two curves, the ZFC curve and the one above it, the FC. The curves indicate a non-reversible process, which could give us the idea of high hysteresis. I will expand on this later. But basically, the general idea is that the distance that separates these curves can tell us that the reasons for the ferromagnetic behavior are fourfold. Basically, we have cationic disorder, tilting and rotation of the octahedron, microstructural defects, and magnetocrystalline anisotropy. So for the first one, the cationic disorder, we initially could expect a cationic arrangement between lanthanum and calcium, but with titanium and iron, that was not the case. Initially, what is inferred from our data is that there are no arrangements of these tiles. As you can see in the top part, there is a certain periodicity between the titanium octahedra and the iron octahedra. Just for clarification, the titanium is blue and the iron are the brown ones. But in our case, we could be having something like the following. In reality, titanium and iron do not follow a specific periodicity, so we cannot determine a global order full order cations in the structure, and this could influence in a considerable way the difference between both curves. For the second part, rotations and tilting and rotations of octahedra, this basically is a no doubt because, as my friend said, we can corroborate with the Ripple analysis carried out that the structure obtained in Vesta shows these inclinations and rotations. So we can attribute this behavior to said phenomena. For the microstructural defects, these cases can include vacancies, interstitial or substitutional defects, precipitates, and impurities that should be expected due to the method that we use, the solid-state reaction. So it is a thing to take into consideration. And the last part is the magnetocrystalline anisotropy. Professor Ra suggested that we review literature on this topic because it seems at first glance that the system might have an easy magnetization axis, but these are studies that will be carried out later due to time constraints, basically, because as you know, if we want to rule out magnetocrystalline anisotropy, we should take measurements of the sample in different directions, something that is costly and really time intensive. But, okay, sorry for a minute. So, different isotherms curves are shown right here in the screen in a range from 50 to 350 Kelvin. We can see that the material in the entire temperature range studied presents a ferromagnetic response. Obviously, it is expected that in range from 300 Kelvin and above, the ferromagnetic response, as you can see in these two last curves, decreases significantly. But it was curious, striking. I don't know a correct adjective to describe that, but it struck us a bit to see that it maintained its ferromagnetic character. Something that we can say with certainty, but we cannot give an exact value due to the limit taken. As you can see in the ZFC and FC curves showed before, is that there is no cutoff point where a clear intersection between both curves is seen. Said intersection is of interest because it tells us the Curie temperature. As you know, the Curie temperature is the limit between the ferromagnetic and paramagnetic transition. However, we can safely state that the Curie temperature for this material is above 300 Kelvin at least. So with the hysteresis curves obtained, we proceed to analyze the ferromagnetic behavior. determining the average magnetization, the coercive field, the remnant magnetization for each of the curves obtained right here. So those data are plotted in these two graphs. As you can see, the feed obtained for both curves confirms that we evidently have ferromagnetic material. If the hysteresis curves were not enough to realize that. But according to literature, if you have ferromagnetic material, it should behave like an inverse exponential function. And that's basically what we have here. That we have an exponentially decreasing behavior. So with all those analyses carried out, we can at a first glance say that CaLaTiFeO6 places itself in a range of being a subferromagnet. And lastly, but not least, we have some last results to share with you, but a little, how can I say, a little warning is that the data that we're going to present right here is data that, I'm not joking about this, we received those numbers like a month or 2 weeks ago. So those these are ongoing analysis that we are performing in this moment. We want to show you these graphs to share the curious things that we are finding, but we are trying in this moment also to understand the physical phenomena that are happening inside of the material. So that's why we are not giving conclusive results about these last two measurements.
Yep. So with the help of Chris Sotelo from Universidad del Norte, we actually made some calculations of the structure, the electronic properties of our structure. In particular, we solved the Consam equations by a plane wave method using the PASP software. The plane waves had an energy cutoff of about 520 electron volts, and we used some. Professor De Luque used a mesh of K-points in the reciprocal lattice following the scheme made by Monkhorst and Pak. With a mesh of 7 times 7 times 5. The calculations were performed following the general gradient approximation, and the exchange correlation energy was studied by the Perdue-Burke-Ernsthoff scheme. And in particular, given that we were working with iron, we added a Hoover correction of 5.3 electron volts to the orbitals of the iron cation. To see the stability of our sample, we measured how we changed the positions of both the calcium and the lanthanum on the cation position, and found that the structure that best or the least energy that had the least energy was the first that you can see at the left, top left. From this structure, we found that the material behaved a little bit like an antiferromagnet. And with this structure, we found, Professor De Luque made the calculations from the bands that you can see at the bottom. And in particular, in these bands, you can see that at the Fermi energy, which is denoted by the dotted line, for up spins, the conduction is different both for up spin and for down spin. In particular, we have a semiconductor behavior for up spin, and we have a conduction behavior for metallic behavior for down spin. So we have a semiconductor ferromagnetic for something that could be used for valve spins, or something that could be used in particular to construct some valves or construct gadgets alike in the spintronic industry. And lastly, we haven't been able to analyze fully the density of states, although it is already calculated. But in particular, in the image, you can see that there is an atypical, in the C part in particular, you can see that there is an atypical behavior for the titanium. it has a prevalence that is similar to that of the iron, and they both are the generators of the ferromagnetic behavior. That would be this part.
Okay, so we also carried out measurements with the help of Jimena when she was doing her postdoc visit. If I'm not mistaken, it was in the Cambridge University. But yeah, 10 measurements were carried out. As you know, transmission electron microscopy is a powerful technique that provides us with detailed information about the structure and composition of materials at the nanoscale. And 10 basically can reveal information about the material's morphology, crystal structure, defects, composition, and more. In this case, the 10 used is one of the Lorentz type. That is, we have a passing beam of electrons through the magnetized sample along an axis, and we are measuring the Lorentz force reflected along the x-axis when the said passing beam of electrons interacts with the material. So as you can see right here, the goal of analyzing this same data is to use software such as ImageG or Python to establish structures such as making an schematic representation, such as walls of ferromagnetic domains or magnetic domains, and establish what is the main characteristics of the magnetic response of our material. From a first glance, we can say that indeed we have some ferromagnetic domains. We can see them in the 10 images, but we also have really polycrystalline behavior. As you can see, we do not have an homogeneous orientation of all the little crystals. We have some ranges where the magnetization changes, not widely, but is something that we have to take into consideration if we want to correctly analyze the physics behind these images. So in a really short conclusions part, because I think that all the things that we discuss in this little presentation are proof enough that we basically have an ongoing but interesting material. First, all methods interesting things. Well, first, it was possible to synthesize a material with quite relevant characteristics using a relatively old method, such as the solid-state reaction. It was possible too to synthesize a material that at first glance seems new, because the bibliographic review that we made at that time of databases to search for possible references about this material was a bit of a bummer, because we could not find anything information. The most closely related papers talk about diluted metals, if I'm not mistaken. So it could be an interesting contribution from this new type of material. But more analysis is needed to determine with certainty what type of material we are talking about, and also to fully understand the interactions within the material in order to explain the behavior observed in the measured responses. We don't know for certain if we have some kind of exchange or super exchange, or I don't know what kinds of bonds could be influencing our response. So those are analyses that we would like to do in order to give a better picture about what are we working with. But basically, to summarize, based on the results presented here, it is possible to affirm that the double perovskite can be cataloged as a ferromagnetic semiconductor, being a candidate for applications in spintonics since its multifunctionality at room temperature allows considering it as an alternative in the design of ferromagnetic transistors or devices based on polarized spin currents, given that that's the final results that we have from analyzing this data. So basically, we would like to make also a short acknowledgements list. Obviously, Professor Jairo Ro, that was the one that gives us this research in the first place. A third colleague from us, Sebastián Rojas, he was the one who helped us through all the sintering process. Professor David Landines and Jimena Velázquez, who also helped a lot, and obviously all the people that helped us with measurements like Milena Saavedra, Miss Miriam, Christian, and all the colleagues from the group. And basically, that was it. Thank you for your time. Thank you for your attention. And we are open to answer your questions.
Thank you.
Bueno, gracias Jesús y gracias Joan por la charla que nos acaban de brindar el día de hoy. Vamos con la parte de la sesión de preguntas. Invitamos también a todos los de nuestras redes que nos siguen por las diferentes universidades para que vayan colocando sus preguntas para nuestros panelistas del día de hoy. Vamos con el profesor. Vamos con el profesor Felipe Mondaca. Profesor Felipe.
Hola, hola. Hola, ¿me escuchan?
Sí,
Hello,
profe.
digo, sí, hola, Jess.
Sí, hola, ¿qué tal? Gracias por la presentación, John. Mi primera pregunta es con respecto a los cálculos que nos mostraron de DFT. Si los pueden proyectar para hacer la pregunta.
Ahí no los está viendo, ya los estoy proyectando.
Sí,
Entonces,
esa.
ahí
Sí, lo estoy viendo. Bueno, hicieron los cálculos con spin, polarización de spin. Mi pregunta es si usaron VAS, ¿verdad? Mi pregunta es ¿en qué átomo ustedes fijaron o les quedó el cálculo, en qué átomo les quedó, digamos, los electrones libres? Esa es mi pregunta. ¿Y cuánto dio la densidad de spin? Si es que esa se corre, si se coincide con lo reportado experimentalmente.
La cosa es que todavía no hemos tenido tiempo de analizar, o sea, de hacer las comparaciones experimentales. Mismamente, por ejemplo, los magnetones de Bohr, creo que también se podrían hallar con el cálculo de FT y también se podrían hallar a través de lo que teníamos de las curvas de histérisis. Entonces, no podría responder esa pregunta en este momento. No sé si Jesús tiene alguna cosita que decir.
Ya, ok.
No, pues el único detalle, sí, como pues dije en su momento, estos son análisis que nos llegaron hace poco. Todavía estamos pues intentando como que entender qué pasa detrás de esto. Y la parte de comparación con resultados experimentales, estamos haciendo los cálculos para ver lo que dijo mi compañero de los magnetones de Bohr. El tema es que pues poseemos, digamos, un poco de problemas por lo que para este material no hay casi literatura, por no decir que no hay ninguna si no la hemos encontrado. Entonces estamos como quedando un poco palos a ciegas, a ver o sea, si logramos entender esto bien para poder explicar ese comportamiento.
Sí, justamente mi otra pregunta era eso. ¿Cómo está el estado del arte de ese material? ¿Dices que es completamente nuevo?
Sí, o sea, lo que nosotros revisamos para este material en concreto, no hay literatura. O sea, precisamente cuando nosotros inicialmente intentábamos entender pues qué es eso de los semiconductores ferromagnéticos, nos salía más que todo eran los semiconductores ferromagnéticos diluidos, no el tema pues concreto que nos interesaba, porque pues si mal no me equivoco, lo que había revisado en esa época era que los semiconductores magnéticos diluidos pues sí tienen comportamientos interesantes, pero también se tiene poco control sobre las fases del material. Entonces me acuerdo que a lo que le achacaban dichos comportamientos eran como esas fases intermedias. Qué sé yo, por dar un ejemplo, sé que esto es un dialéctico, pero por dar un ejemplo, cuando uno sintetice un MgTiO3, la literatura dice que te van a quedar trazas de MgTi2 o 5. Entonces, decían, o sea, los semiconductores magnéticos diluidos decían que esas fases intermedias pueden estar presentando los comportamientos que a uno inicialmente le interesan, pero que lamentablemente como pues es como complicado controlar que esas fases no se den, pues no es algo muy reproducible. En el caso de lo poco que encontramos de los semiconductores ferromagnéticos, las características se dan por la interacción completa de la estructura, pero particularmente sobre este material no encontramos literatura de ningún tipo. O sea, sí habían otros materiales reportados, pero no específicamente para este.
Ya, ok. Y mi última pregunta. ¿Cierto que hicieron mediciones del bandgap con espectroscopía óptica o reflectancia difusa? No me quedó.
Sí.
Entonces, claro,
De,
ustedes tuvieron un valor de 1,6 electronvolt, creo, o menos. No me acuerdo bien el valor.
ahí
0,6.
está 0,6.
Ajá. Si lo comparan con el bandgap, digamos, porque ese es el óptico. Si lo calculan con el electrónico, porque no escuché bien el número que obtuvieron con el
No, también mencionamos
electrónico.
eso.
Pero un segundito.
¿Cuánto les dio por
Un segundito que se
por
me
el
pasó por
cálculo de
completo.
DFT?
Ese dato sí
Se
lo
me pasó
tengo
por
yo.
completo mencionar, espérate, estoy abriendo el Word, que se me pasó por completo poner. El gap nos dio de 0.57 electronvoltios.
Ya, ese es para el lab, ¿o no? O para el... Y para el
O sea,
down.
Espérate que no
Porque
tenemos
como
el
son distintos,
otro.
¿no?
Sí, pero o sea, la cosa es que en el app, bueno, sí, no sé, la verdad es que aquí solamente tenemos un valor de 0.57, entonces no sabría, creo que es el promedio, sí.
Ya.
Entonces,
Sí, porque como tienen dos gráficas, ¿no es cierto? Para los up y para los
sí.
down. Y mencionaron ahí que uno era comportamiento semiconductor y el otro era conductor. Claro, yo esperaría dos bancas, ¿no es cierto? Ahí
Sí.
en el medido, o sea, digamos, ahí el que tienen ustedes, pero no sé si eso es correcto. Esa era mi pregunta. No sé si
Pues no,
en su gráfica tendrían que esperar dos gráficos, dos bancas, o no. Esa era mi duda.
no sé si, o sea, ahí sí no sabría comentar, pues tal vez, o sea, diciendo, pues como que una intuición es que, pues sí, tal vez lo que estemos observando en el gap óptico sea el promedio de los dos band gap. Tocaría analizar con cuidado a ver pues sí, poniendo estos datos con cuidado, ya tomando lo que tenemos de DFT, pues podríamos encontrar ya haciendo un mejor feeling si tenemos otros band gap. Pero en principio pensaría que lo que observamos en el band gap óptico es el promedio entre los dos. Pero con Lega ahí sí no
Ya.
estaría del todo seguro.
No, bien. Gracias por la presentación.
Gracias
Gracias
por
por
la
las
pregunta.
preguntas.
Hasta luego.
Muchísimas gracias, profesor Felipe, por sus preguntas. Vamos ahora con el profesor Sergio Conejeros. Profesor Sergio.
Hola, ¿qué tal? Buenos días, desde aquí de Chile. Gracias por la presentación, Jesús y Joan. Gracias por compartir sus resultados. Yo tengo algunas preguntas, principalmente cuando ustedes hablan de nuevo material, ¿a qué se refieren con nuevo material? Porque este compuesto ya ha sido reportado en la literatura ya. En el 2013 fue reportado este compuesto.
Seguro, profe. Pues ya nosotros buscamos y no
Sí.
encontramos, o sea, experimentalmente no encontramos ningún
El mismo
reporte experimental.
con el grupo espacial 14, exactamente el mismo grupo que encontré. Por eso, o sea, yo les puedo mandar, sí, lo tengo, o sea, que lo tengo.
Sí, por favor, profe.
Entonces, en base a eso, ustedes, ¿cierto? Este compuesto, es que yo más o menos trabajo con este tipo de compuesto y trabajo con compuestos que tienen el grupo espacial 14 normalmente. Y para este tipo de dobles perovskita con grupo 14 siempre hay ¿cómo se llaman? Se comparten posiciones, ¿ya? el factor de sitio de ocupancia, normalmente las posiciones weak son compartidas. Entonces ustedes pusieron muy bien el calcio y el lantano, pero el titano y el hierro también comparten posiciones. Y eso lo complica todo. ¿Por qué lo complica todo? Porque el titanio es diamagnético y el hierro no, el hierro es magnético. Entonces, si ustedes no tienen un ordenamiento claro para los átomos de hierro dentro de la estructura, o sea, si no lo saben, eso complica el análisis, particularmente porque ustedes no sabrían en qué posiciones se ordenan los hierros. O sea, si hay un 50% de que se ordenen los titanios, 50% de que se ordenen los hierros de manera... Eso lo podrían, por ejemplo, ver con cálculos computacionales, pero no con los cálculos que ustedes están haciendo ahí, sino con algún Monte Carlo que más o menos les dé la distribución o le busque la distribución más precisa, o tratar de buscar, ¿cierto?, con algunos pocos cálculos de manera inteligente si a los hierros les gusta estar juntos o si les gusta estar de manera aleatoria. Eso lo podrían ver, pero el titanio y el hierro también comparten posiciones, ¿ya? Entonces, cuando ustedes hacen las curvas de susceptibilidad magnética, eso también es curioso, y ahí hay un análisis. ¿Han escuchado hablar de estas transiciones tipo vidrio de spin?
Sí.
Entonces, cuando las transiciones de vidrio spin, si ustedes, ¿cierto?, bajan la temperatura, van a tener un comportamiento ferro, siempre que va a ser distinto a baja temperatura, claro, porque si ustedes tienen los hierros de manera aleatoria, siempre no van a tener la misma magnetización. Entonces, eso sería interesante de observar. Hay algunos análisis experimentales que se dedican a ver ese tipo de comportamiento cuando ustedes tienen comportamiento del tipo de vidrio spin. Ustedes empezaron a medir como de la temperatura del nitrógeno líquido en adelante, ¿cierto? Sí, o sea, como de 70 y tantos Kelvin en adelante, igual tendrían que ver la posibilidad de colaborar con alguien que les mida la susceptibilidad magnética a más baja temperatura, a ver si pueden ver un comportamiento, ¿ya? O sea, este un nuevo material no es, pero sí lo pueden usar como punto de partida para hacer otras cosas, ¿no? Igual puedes tratar de hacer sin fin o hacer otro tipo de cosas con este tipo de materiales. El hierro, ¿qué midieron el momento magnético para el hierro?
No tengo ese dato porque yo...
O sea, porque el hierro es el centro magnético, pero el hierro es hierro 3+, es decir, tiene 5 electrones desapareados, pero puede ser de spin alto, con los 5 electrones desapareados, o puede ser de spin bajo, con un electrón.
Sí, estamos intentando...
Entonces, si ustedes miden, ¿cierto?, si ustedes miden la magnetización a temperatura ambiente, pueden darse una idea de cuánto es el momento magnético, y ese momento magnético ustedes lo cuadran, hay una pequeña fórmula que les da el momento magnético calculado. Creo que si es 5 electrones es 4, y algo, 5, y algo, y cuando es un electrón es 1,73, por ejemplo, cuando tienen un electrón desapareado, un D1 o un D9, ¿ya? Entonces ahí pueden saber fácilmente si tienen hierro 3+, y de bajo spin o de alto spin. Y eso es importante para los cálculos. O sea, cuando ustedes hacen el cálculo de es un poco por ahí va la pregunta de Felipe, porque ustedes con qué hierro, ¿cómo hicieron el cálculo? ¿Con hierro 3+, pero cómo fijaron los electrones desapareados? ¿Pusieron un electrón o pusieron 5? ¿Cómo hicieron el cálculo?
Apenas estamos seguros.
O le dieron que el programa hiciera lo que él quisiera. Eso también es peligroso porque normalmente cuando ustedes hacen eso, les produce un artefacto, ¿ya? Y les da una solución que muchas veces no tiene significado físico. Entonces, la mejor forma de ver eso con el cálculo es hacer un cálculo sencillo. Ahí pueden asumir, decir, bueno, un cálculo con la celda primitiva, con la celda convencional, poner cómo asignaron. Es decir, bueno, vamos a asumir que están de manera aleatoria los hierros y los titanios, 50% hierro, 50%, la forma más ordenada solamente para ver los estados de oxidación solamente para ver el spin del hierro. Entonces, ¿qué programa usaron?
Para el cálculo de FTC, VASP.
Y VASP le permite fijar los electrones, ¿no? Es decir, quiero hacer un cálculo con con 5 electrones desapareados y hacer un cálculo con un electrón desapareado, pero no solamente que me tome la configuración inicial, sino que lo mantenga durante todo el cálculo SCF. Entonces ahí ustedes pueden comprar las dos energías y pueden saber si es hierro, tienen un electrón desapareado o tienen 5 electrones desapareados.
Sí, le estaba adelantando.
El que tenga la energía más baja. Pero es importante, es sumamente importante, por eso cuando Felipe le preguntó eso, ustedes eso deberían saberlo, porque si no, el cálculo de FT puede dar cualquier cosa.
Vale, profe. Gracias por la recomendación.
Gracias.
Tengo más preguntas,
gracias.
pero tengo que dejarle tiempo a los otros panelistas, pero gracias por su
Sí,
presentación.
tranquilo.
No, gracias.
Listo, profe, gracias por la
Gracias.
recomendación. Que sí.
Muchísimas gracias, profesor Sergio. Vamos, bueno, nos comenta el profesor Arturo que no tiene preguntas. Vamos con el profesor Stuart. Profesor Stuart, are you there?
Thank you, Jesús and Joan, for your nice talk. I have just some simple questions. It's very interesting material from a spintronics point of view. As you mentioned, you have the band gap for one of the spins. The spin, I think it was spin up. Spin up had the band gap, so it has a so-called half metallic behavior. In your measurements, did you see any evidence for that? Maybe the magnetic moment was an integer or close to an integer? Did you have any evidence for the half metallic behavior?
Responde tú,
Direct evidence.
Responde, Jesús, please.
Okay. Direct evidence? No,
like an integer magnetic moment.
Yeah, the DFT calculations show that our magnetic moment for the initial calculations is 10.0 micromagnetons of Bohr.
Yeah.
But we are making the calculations by hand to compare the calculations from the DFT program to the real data that we can measure from the magnetic moments. But we will not be able to measure the direct magnetic moments to compare with the safe value that the DF program shows us. But yeah, at least in the theoretical calculations, yeah, it's 10.0.
Okay. I think also to develop the technology of the material, you would have to make the material in thin film form. I know you're making a bulk crystal. Do you have any thoughts on how you could make the material in thin film form? Maybe on a silicon substrate or something like that? Is there a process you could develop?
But at the moment, we have not thought about a thin film version of CaLaTiFeO. I think that we are developing new materials, but using the Pecini technique now in the group.
Yeah.
But we will have to talk with other groups that are specialized in thin film deposition.
In our group, we do not have the equipment. We don't have vacuum or sputtering. We mainly have the photosis, so we would need to speak with another groups in order to produce the thin films.
Yeah, I mean, you might be able to enhance some of these half metallic properties in the thin films. You might be more in control, maybe, of their properties. Maybe.
Yes.
Okay. Thank you for your talk. Very interesting. Thank you. Thank you again.
Professor.
Thank you for your.
Thank you for the questions.
Thank you, Professor Stuart, for your question. Now, ahora vamos con. Vamos entonces ahora con nuestros invitados. Hugo Cabrera.
Buenos días, ¿cómo están? Buenos días, Joan.
Hola, profe.
Primero felicitarlos, estuvo muy interesante su charla.
Hugo, para que por favor la cámara para la pregunta. Muchas gracias. Gracias.
Sí, bueno, ya se hicieron bastantes preguntas sobre la parte de FT, pero de todas maneras me quedé un poquito curioso. De repente el material no ha sido tan estudiado, ¿no es cierto? Quería saber ¿cómo así obtuvieron la estructura, ¿no? La estructura inicial para los cálculos en DFT. Eso me quedó un poco curioso.
Digamos que para hacer el refinamiento Ripple primero necesitamos el modelo, y el modelo lo obtenemos por un software que se llama SPUTS, que es básicamente un software que permite, o sea, digamos que a partir de cálculos geométricos permite simular posibles estructuras que pueda tener, pues en particular, compuestos de tipo perovskite. Entonces, digamos que comparamos diferentes tipos de modelos que daba el software en particular. Digamos que miramos también, o sea, ordenamientos de perovskita simple sustituida o de perovskita doble con ordenamiento de tipo SAL. Y pues la que más ajustada fue la que nos dio la monoclínica del grupo 14 que mencionaba el profesor hace un ratico.
Sí. Ah, ya, o sea que, digamos, en la parte experimental ustedes refinaron, ¿no? Hicieron ese...
Sí, hicimos el refinamiento
Sí, sí.
Horrible, ya, entendí, y ahí obtuvieron la estructura, ¿no? Ok. Ujú. Ok, básicamente era esa mi pregunta, creo que ya era
Vale, profe.
Vale, gracias.
Gracias, profe.
No.
Muchas gracias por la pregunta. Vamos ahora con Maggie.
Hola, buenos días.
Buenos días.
Gracias.
Bueno, muchas felicidades a los chicos. Si entendí bien, ¿son de licenciatura? ¿Es su tesis de licenciatura? ¿O de qué son?
Estudiantes de maestría.
De maestría. Bueno, igual, pues muchas felicidades. O sea, están muy jóvenes. Yo nada más tengo, bueno, una observación en la diapositiva 20. Me quedó la duda si estaban reportando emus por gramos o emus. Bueno, ahí dice emu.
Emus por gramo.
Entonces le falta ahí los gramos.
Sí, me falta.
Ok, sí, porque ya se me hacía raro los valores. Bueno, y una sugerencia, o bueno, no sé si les puede servir hacer estudios de AFM con la punta magnética. O sea, hay estudios de microscopía de fuerza atómica donde puedes poner una punta magnética y te mapea los dominios, ¿no? Entonces, pues vas a diferenciar entre los dominios que son magnéticos y los que no lo son a nivel nano. Entonces, pues eso les podría ayudar. Bueno, no sé si les podría ayudar. Pues pueden mapear eso y pueden mapear también con otro tipo de punta la función trabajo. No sé si eso también les pueda ayudar a entender su material. Si no tienen por ahí, acá encima se tienen esas técnicas en el equipo de AFM. Es mi único comentario. Muchas felicidades.
Vale, muchas gracias.
Muchas gracias.
Muchísimas gracias por la sugerencia. Bueno, ya no tenemos más preguntas de los panelistas de acá. Vamos entonces ahora con preguntas del público. Bueno, James tuvo problemas y tuvo que salir, pero no sé si de pronto desde el profesor Arturo en el Simvestat de México hay alguna pregunta.
No tenemos por acá.
Gracias, profesor. Por último, Vanessa, ¿hay alguna pregunta de la Universidad Nacional de Colombia? Muchas gracias, Vanessa. Bien, ya podemos dejar de compartir. Pues agradecerles por la charla que nos brindaron el día de hoy. No sé si quieran decir algunas palabras de despedida.
No, muchas gracias por las correcciones y por los comentarios, pues todo eso igual sirve para aprender, para ver si pues entendemos bien lo que pasa y también aprender cómo hacer estas cositas bien. Pero muchas gracias por la atención y por todos los comentarios y las preguntas.
Sí, pero muchas gracias por tenernos aquí en Seminario Internacional. Sí tenemos pendientes un par de medidas y un par de calculitas, pero gracias por las correcciones y por las sugerencias. Nosotros pendientes de todo.
Bien, encendemos nuestras cámaras para pues despedir